Hi everyone. In this lab, we are going to cover analysis in three dimension using ANSYS Workbench, and here are the contents that I'm going to cover. We will start by modeling a beam bracket in Design Modular and create a 3D model, and then we will convert or create a copy so that we can create a surface model based on that, and will solve both 3D model and surface model in ANSYS, and finally we will compare the results using both of these models. So 3D model and surface model are both different modeling techniques that we can use to analyze a complex object or a product in ANSYS Workbench. And finally, there is this one assignment that I'll guide you about. So here we have the dimensions of a beam bracket. You can see that the dimensions of the base are provided. Apart from that, we have the dimensions related to the web of the bracket. So this bracket can be attached to the wall from the back side here, the flat side, which is right behind this. We have the dimensions for fillet, thicknesses, base thickness, and web thickness. First of all, what I'm going to do is open the workbench and will model this, and then after modeling we are going to convert the model to surface model and then apply the required boundary conditions that we have, and finally we will solve it for the stresses and the total displacements. Here you can see the beam bracket. It is made of structural steel. The support that is applied is the fixed support at the back face, and the maximum load that is supposed to be applied is 27 kilonewton. Let's shift to ANSYS Workbench. Okay, I'll start with static structural module of the ANSYS. Let's rename this to 3D model. The first step is to specify the engineering data or material properties. So it is mentioned that the bracket is made of structural steel, and here we already have structural steel in our engineering data, so we can use this in the model for further analysis. So nothing to change here. We have all the properties: Young's modulus, Poisson's ratio, yield strength, compressive yield strength, and other properties are all here. We can move on to modeling the geometry. Since we are performing the 3D analysis, make sure that the analysis type is set to 3D in properties tree of the geometry. So I'll model the geometry in Design Modular. After opening the Design Modular, let's start by modeling the base of a beam bracket. Let me look at the dimensions. So the base is of 140 millimeter by 180 millimeters. So first we need to change the units to millimeter, and I'll shift to XY plane. The base is simply a rectangle with dimensions of 180 millimeter and 140 millimeter. So it's better to make this base symmetric around x-axis and y-axis. So I'll make this symmetric. So under constraints, we have this symmetry option. And in order to specify the symmetry, we can select the axis of symmetry first and then the lines or the points that we want to be symmetric. We can select this again and make this symmetric about these x-axis as well. So next step is to extrude this by base thickness is 16 millimeter, so extrude this by 16 millimeters. So this is the sketch. We are going to add the material and I'll extrude this to 16 millimeter from the base and generate this. So we have this base ready and we can further create the web now. In order to create the web, I'll shift to the YZ plane. So this is the central plane here and draw the sketch. So the sketch is simple and it starts exactly at the top face here. So we can draw this sketch using the line feature or polyline feature. We will start with using the polyline feature here from this point. So the first line is horizontal, then there is a vertical line. After that, we have angular line, and then there is another horizontal line. And finally, I'll right click and press close end. So the sketch is closed using the polyline feature. And now I can apply the constraints to make sure that everything is all right. So the first thing is this line is vertical, this line is vertical. Secondly, these are the horizontal lines. And finally, the dimensions. So this dimension here is 140 millimeter and this is symmetric about the y-axis. So I'll apply the constraint. So this line is symmetric about this vertical axis. Secondly, we have the total height, which is 164 millimeter. So this is 164 millimeter and this 164 millimeter is actually you see it just moved downward, so this is above this horizontal line. So in order to do that, I'll just delete this dimension. I'll just redo the process by pressing Ctrl Z, and first I will specify the dimension between these two lines. So I'll click on the edge and the horizontal line by pressing the control, and we can specify this to be 16 millimeter, which is the thickness of the base plate. Now V2 is 164 millimeter. This goes just above the line. 20 millimeter and 20 millimeter. So these are the other two dimensions. The remaining two dimensions are 20 millimeters. This is 20 millimeter and this is also 20 millimeter. So the sketch is fully defined and you can see that this sketch is exactly at the center of the base plate. This sketch can be extruded using the extrude feature, and the thickness of the sketch is 10 millimeter. So we want this web to be exactly at the center of the plate. In order to do so, we can use the extent type here instead of direction vector. So we can use this direction vector as both and symmetric. So you see for now the dimension is 16 millimeter. So what it did, it created 16 millimeter on the left side of the plane and 16 millimeter on the right side of the plane. So the total thickness is 10 millimeter. I'll just specify 5 millimeter here, and then create the sketch. So since I created the sketch exactly at the top face by specifying the dimension, now this additional body, it is the additional body created, it just became the part of the base. So this is the initial sketch that we have. Finally, we can specify the fillets of the corners. So here, if I look at the beam bracket, so we have two fillets at the corners and two at the center. In order to specify the fillet, we can use the blend feature and fix radius option here and select the corners where we want the fillet to be applied. So like this, apply, create this to be 16 millimeter and generate. So we have the geometry ready for the analysis. Let's move on to the next step in the analysis, which is specifying the boundary condition and solving for and creating the mesh. The geometry is imported automatically in the analysis tab when we open it. And if we look at the material structural steel is assigned by default. So this is the material that bracket is made of. The next step is to create the mesh. So I'll show you the multiple settings and methods that are available in Workbench to create the mesh. So first of all, let's start with creating the uh, general mesh with default settings. I'll just generate the settings, and here we see we have tetrahedrons actually uh, as a part of the mesh. So we can refine this here to fine, medium, and coarse. I'll just generate this. Now we have a lot of tetrahedrons, and the mesh method that we use is adaptive. By adaptive means wherever the refinement is required, the program will automatically refine the mesh. So you see near the fillets, there is a bit of high density for mesh. Uh, yeah, so there is this high density mesh in the region of fillets. So why is this a 3D mesh? You see that in all three dimensions, like here, if I look at this particular face, we have multiple elements. And in the other two dimensions, we also have multi-dimensional element. And we can look at the some matrix. Let's look at the quality of the mesh here. When I click on any of the bar, we see that the elements having the quality which is about 0.78 maybe or 0.8 about here. So all of these elements here, they are tetrahedrons and that are represented by this mesh. If we move to higher quality, these are the higher quality meshes and these are the low quality mesh elements. So we see the distribution of all the mesh elements here using the mesh metric. Similarly, we can look at the aspect ratio here, which is almost 2.2. So there are elements with having very large aspect ratios, like one or two elements here. So they have very large aspect ratio, which is not desired. Okay, let's look at the different mesh methods that are available here in ANSYS. So the first method, if we look at is, I'll just simply select the geometry, apply this. Under the methods, we have tetrahedrons, we have hex, dominant method, we have sweep method, and we have multi-zone method. So these are the four different main options that are available in ANSYS for the meshing. We will look at all of these one by one. So the tetrahedrons, if I click, we can use tetrahedron using the patch conforming method and patch independent method. So the difference between patch conforming and patch independent method is if there is some imprint on the face. So patch conforming method will start mesh around that face and will respect the boundary of the imprint. However, patch independent method, it is a volumetric meshing technique, and it will just neglect the features that are simply imprinted on the face. So when I create the mesh using tetrahedron, so we already have a tetrahedral mesh. So there is not a big difference here. The next method that we can use is the hex dominant method. So we have seen in the previous video for 2D meshing that the chord elements, they are more accurate as compared to the triangular elements. So same is the case here in 3D, where the hex elements, they will provide much more accurate solution as compared to the tetrahedron mesh. So hex dominant method, so ANSYS will try to enforce the chord element methods based on this geometry. So when we create this, so this is the hex dominant method, and if I look at the mesh with adaptive technique, you see that some of the elements here, majority of the elements, they are hexahedral elements, but there are few maybe which are of tetrahedrons, or maybe all of them are hexahedral mesh. You can change the size function from adaptive to curvature, and you will see the difference of the meshing techniques here. So you see, when we are using the curvature based meshing, the mesh quality is much better and the mesh is quite structured. However, I see here we still have some uh, tetrahedrons that are coupled with the hexahedral mesh elements. So you see, the curvature based mesh, it provides a better and uniform mesh. So if we move this, we can use all chord here as well, like we did in the 2D analysis. The next method is to use the multi-zone method. So what is multi-zone method? So in multi-zone, ANSYS will try to convert the mesh into hexahedral meshes for the whole body. So I'll let you know what it means. So if you click what it means, if I click here on the mesh and under preview, under show, if I click on the sweepable bodies, okay, let me delete this. I'll just generate the mesh, and after generating the mesh, I can review whether the body is sweepable or not. So when I click on sweepable, so there is, the body is not sweepable here, so it is difficult to create the hexahedral mesh manually. So what it means by sweepable mesh, sweepable meshes are those where we can simply create the rectangles or chord elements on one face of the object, and then simply by extruding those elements we can recreate the whole body, so that body is sweepable. Here we cannot perform such an analysis. What uh, so if I insert the method, click on the body and apply the multi-zone method. So what multi-zone does is it simply divide the body automatically into multiple sweepable bodies, and then those sweepable bodies can be extracted to create the hexahedral mesh. So when we generate the standard multi-zone mesh, you will see that this is much more better here. So here we have the hexahedrons or chord elements on the faces, and those chord elements are simply extruded inside. There are some changes as well here, but majority or almost all of the elements are chord elements here. So this is used for the complex body meshing. And here you can specify different parameters like the element order or manually select the faces as well. Let's change the method to the sweep method, and in the sweep method you need to specify the source and target of the uh, sweepable body. So the source is the face at which we are creating the chord elements, and then the target is the face at towards which we are extruding those chord elements. So let's see if it works for this. So this is the manual source, and if I select this face and uh, change this to manual source and target, so the target is this one. Let's try to create the mesh. So we cannot create this mesh using the sweepable body because uh, the geometry is changing drastically. So in this case, we have to use the multi-zone method actually. So multi-zone is the best option in this case. I'll just generate the mesh. Now using this multi-zone method, you see, and the curvature based setting, this mesh is perfect actually. And all the elements, they are chord elements. The quality, if we look at aspect ratio, this is about 1.8, much better, and element quality is about 0.8, so this is above 80%. So this is an example of a good mesh. We can further refine the mesh applying the other controls like the sizing and refinement or face meshing, and this will further refine the mesh in the regions where we want. But beware that you must not use a settings that will create a large number of elements. So here we have 63,000 nodes and 13,000 elements. So this is quite good. So less than 30,000 elements, this is considered as a good mesh that can be solved with current computing power that we have. So this was about the details of 3D meshing. We will now shift to the boundary conditions. So the boundary conditions in this case, they are quite simple. We only have two. The first one is this bracket. It is fixed from the base or from this right edge. So we can insert the fixed support boundary condition and select the face which is fixed. The second boundary condition is the force which is acting downward on the face, and its magnitude is 27 kilonewton. The force is acting downward, and this is minus 27,000 newtons. If we look at the coordinate system, here the force must be in positive z direction. So this is now acting downward. And if we look at the post processing, I'll show you few details that we have. The first one is the equivalent stress. So equivalent stress here, we can see that there is von Mises written in the bracket here. So this will show us the stress based on the distortion energy theory that we learn in the materials course. The second option is the maximum principal stress, middle principal stress, and minimum principal stress. So when we draw the Mohr circle, you see that there are two principal stresses associated with each point in the body, and actually the three principal stresses that are associated each point in the body, and the fourth one is the maximum shear stress. So these four parameters, they are based on the Mohr circle for 3D objects, or for the 2D problems that we solve. Then this is the stress intensity factor. Normal stress and shear stress we can find in any directions that we want to specify. If I move on to the strain, we have similar properties associated with the strain. Equivalent strain, which is based on the distortion energy theory, maximum principal strain, middle principal strain, minimum shear, then the strain intensity, normal and shear strains in any directions that we want to find. And if I look at the deformation, so these are the two different deformations. So the first one is directional, in which we can use x, y, or z coordinate, or the total deformation, which is the combination of all of these uh, different coordinates x, y, and z. Moving on to the stress tool, here, we can calculate the safety factor based on different theories that are available in materials, mechanics of materials. So the first one is the distortion energy theory. And if I insert here, you will see that a stress rule and the associated safety factor is inserted. For calculation, it depends on which theory we want to use. The second one is the maximum shear stress theory, which is also a part of materials course, and the safety factor is calculated based on those. So the maximum shear theory and distortion energy theory, they are usually used for ductile materials. Then we have Mohr Coulomb stress, which is used for the brittle materials, and maximum tensile stress theory. So the stress tool can be used to calculate the safety factor. There is one parameter that you need to take care of when calculating the safety factors, and that is you must specify the yield strength of a material under material properties. Previously, in the previous lab for 2D analysis, we only specified two properties: the elastic modulus and the Poisson's ratio. However, if we want to calculate the safety factor, we must also add the yield strength of the material under material properties so that it can be calculated. Furthermore, we have a fatigue tool, and we can analyze the uh, part under different fatigue loading as well, and simply inserting this fatigue load will solve the system for fatigue loading. And we can use different criteria that are available, like the Soderberg criteria, Gerber criteria, or Goodman's criteria for calculating the fatigue stresses here. And then there are some other tools that are not a part of this lab, which includes the bolt tool and the contact tool, which they can be used for bolt stresses and other parameters related to bolts and the contacts. Finally, we have the probe. We can use these probes to calculate either the deformations, positions, angles, energies, and also the reaction forces at the supports as well. So in this case, we want to find the equivalent stress, equivalent maximum stress, and also let's say we want to find the maximum principal stress and see the difference between these two and the maximum deformation. So this is the total deformation that will occur in the body. And I can calculate this by hitting the solve button. After the solution is completed, the results are available to review. Here we have the safety factor. You can see that the safety factor is minimum at the fixed support near the fillets, and it is maximum in this blue region. So the minimum safety factor is 2.8, which occurs near the fillet at the support, and we can view this minimum and maximum by switching on the probe button here. Let's move to the equivalent stress, which is the stress calculated using the shear stress theory, and you see that this equivalent stress is 88.74 megapascals, and the stress is maximum where the safety factor is minimum. Finally, we have the maximum principal stress, which occurs at the corner, and this is 97 megapascal, which is higher than the equivalent stress, although the safety factor is calculated based on the equivalent stress. It's because the material is ductile and we are using the distortion energy theory, which which combines the three-dimensional state of stress to a 1D stress and provide the result. So that's why we are using the equivalent stress here. The final parameter is the total deformation, which is maximum at a point which is far away from the fixed support here, and it is 0.09 millimeters. Also, you can see that the results, they are symmetric about the YZ axis, so we could have solved the problem using the symmetry condition as well, and it would have given us the same results. Also, this safety factor is calculated based on distortion energy theory, and this is the stress based on distortion energy theory. However, if you want to find the stress based on the maximum shear stress theory, the stress is mentioned here with the name of intensity. So we can retrieve these results and review the values for the safety factor and also for the stress intensity that we have. As expected, the minimum safety factor in case of stress intensity or maximum shear stress is 2.5. However, the minimum safety factor is 2.8 in case of distortion energy theory. Here, the maximum stress is 99.77, which is greater than the maximum principal stress. So you can see that the maximum shear stress theory is much more conservative as compared to the distortion energy theory. And finally, we can analyze the fatigue response of the system. So we have applied the force, which is of 27,000 Newton, and we can select the criteria for under which we want to analyze the system. Let's say that we want to analyze for the Soderberg criteria and apply the different fatigue ratios or fatigue cycles. So zero base fatigue cycle, here you see the minimum does not go to below the zero. Similarly, fully reversed means that we have complete sinusoidal wave. Here we can specify the ratios, loading ratio between -1 and 1, and finally we can specify the historical data based on the location and insert the tabular data from the files. So I'll go with the fully reversed cycle. This is the scale. The scale is like So we are applying 27 kilonewton on the bracket. So let's say the force is 2 times or 3 times, so we can change the scale factor for the fatigue uh, cycles. We can use two different methods. The first one is the stress life method, and the second one is the strain life method. So on the stress life method, we have different theories and criteria that are available. We can use Goodman criteria for our analysis, or Soderbergh criteria, which is the most conservative one. And stress component could be the maximum principal stress, or it's better to use the stress from the distortion energy theory. And that's all. So we can retrieve the results. Uh, Before retrieving the result, we need to insert what we want to find. We may need to find the safety factor, or we may need to find the damage or equivalent alternating stresses. So these are the other parameters that are used for fatigue analysis, that include the rainbow matrix and damage matrix as well. So the most familiar thing is the safety factor in fatigue. So we can analyze the system for cyclic loading under 27,000 Newton, and you see that the minimum safety factor is less than 1. So this bracket will fail under the fatigue loading. And the minimum safety factor is again at the same point. Design life is 10 power 9 cycles. So this is how we can look at the results from the fatigue. Let's move on to the other method of solving the same problem using the surface model. So in order to use the surface model, I'll just close this project, and I'm going to duplicate this whole analysis that I have. So once the analysis is duplicated, I'll just rename this to surface model and open the geometry. After opening the geometry, we can convert the solid model that we created into the surface model. There are two ways to do this. The first one is to simply delete the fillets, extrudes that we created, and using the sketches that we have here, and create the surface from the sketches. This way we will have the base sketch for the surface model that we are going to analyze. So another method is, if we have the solid model, is to use the mid surface tool from the tools, and we can select the pairs here. So this is the first face and this is the second face. So these are the two faces. I'm keeping the control pressed while clicking on these. So these two pairs we have selected, and the mid surface between these two will be selected. The next one is this top face and bottom face. So this is the second pair. So it will create this surface. And the third one is the right face and the bottom face. So we have three pairs that we want them to be converted to surface. And when I'll click on apply and generate, you will see that a simplified surface model of both bodies are created. And if you look at the tree, you see that two different bodies from a single solid part. And simply by converting this, you see that we have this generalized model of the surfaces. In this case, you can see we are not modeling any fillets. So this is the first difference here. We are not modeling any fillets, and we can change the views to see the cross-section solids if we have, but for now we don't have any, and other wireframes and exterior shades. So I'll just click the close button and go to the analysis tab here. First of all, I'll update this whole model, and then I'm going to open this. After updating the model, I can click and open it so that we can go to the analysis tab and analyze the details based on the surface model. Here we have two different surface bodies, and the thicknesses they are automatically detected from the solid model that we created. So this is 16 millimeter and this is 10 millimeter. The next step in the analysis is to create the mesh here. So when I go and click on this multi-zone, for now we haven't selected any bodies, so I'll need to select these bodies for the multi-zone and then generate the mesh. Let's see what kind of mesh is being generated. So this is a good mesh, but this is not fine actually. So we can make this a bit, we can refine this a bit and change this settings to. So for the surface models, you see that we only have these three options: multi-zone, triangles, and chord dominant. So I'll change this to multi-zone and regenerate the mesh. So I'll try to use all chord mesh for this analysis. Let's generate this. So we have all chord mesh, but the number of elements, they are very small in this case as compared to the 3D model, a full 3D model that we previously used. And finally, I can change the size function here to adaptive or uniform maybe. Let's say that with uniform settings, we have almost a similar kind of mesh. So let's define this a bit using the relevance center and generate the mesh. So this is refined one, and one difference that you may have noted is uh, along the thickness of the surface, we only have one element. You see that along this plane we have one element, one element, one element, one element. However, when we are modeling for 3D analysis, we can have multiple elements in the thickness direction. Same is the case here. In this x direction, if I look at, we only have one element which is extruded along the length. So all of these elements, they are chord elements now that are extruded. We need to redefine the supports here and select the corners here instead of the edge, instead of the face. So we select these three corners and the force is applied at this face actually and this face. So these are the two faces where the force is applied, the direction is same, and we can solve the problem using the surface model. Here we have the maximum stress which is occurring at the intersection of the two surfaces. Maximum principal stress, if I look at the safety factor here, in this case the minimum safety factor is 3.3, and if we look at the other safety factor which is 3.27 based on stress intensity, and finally the fatigue safety factor is 1.14. So here at the junction we are getting some random results, and we have this loss of information that occurred while using the surface model. Surface models are usually used for very complex shapes, like maybe a vase or something that we cannot model, or if the thickness is very small in 3D space for a complex geometry. So surface models are better for those models. So this is how we can use the surface model for analyzing the information that or the part that we have. Moving on, this is the assignment that you can perform and practice with. So here the material properties and dimensions are assigned. You need to solve the problem using the full 3D model, then the surface model, and then the half 3D model. So this is symmetric. And here there is one boundary condition, which is the bearing load. So instead of applying the forces, you need to specify the bearing load, which is the part of the structure analysis. So this is all about this lab. And thank you so much, and I will be back with the next lab soon.